have known for a long time that temperature is the measure of the kinetic energy of molecules. But we've always been kind of cagey about what exactly we mean by that. It turns out that it takes some messy statistics to get there, but the kinetic energy of a molecule is 3/2 times Boltzmann's constant times temperature, 3/2 kBT. And that's for one molecule. So that is something where you could set that equal to 1/2 mv squared and figure out the speed of the molecule as long as you know the temperature, keeping in mind that temperature is for an average. All these molecules are moving at various speeds, but they average to that one speed. So you could find the average kinetic energy of a molecule. That means that if we know the average kinetic energy of each molecule, if we know the number of molecules, we can figure out the total amount of energy in a gas, what we call the total internal energy. And it works like this. The kinetic energy of one is 3/2 kBT, and then the number we have is the number of moles times Avogadro's number. But Avogadro's number times Boltzmann's constant is the universal gas constant, and combining all that together means we get U equals 3/2 nRT. The total internal energy of a gas is 3/2 times the number of moles times the universal gas constant times temperature. This equation is not on your reference tables, and it is absolutely critical that you memorize it. You're going to need it, and it's not there, so it's got to be here. U equals 3/2 nRT, the total internal energy of a gas, 3/2 nRT. Memorize it, please. All right? I think you've known for a long time that when you heat things up, they expand. This is true of pretty much every material except water right near the freezing point, which is an interesting exception. But anyway, this is the foundational technology of, say, thermometers, right? This is why bridges have expansion joints, so that when they expand and they contract, you can still drive over them without them buckling in some way or another. We'll do an example problem on that one to see just how big that problem can be. It's a technology we use in thermostats, for example. If you have an old school thermostat before computers were even invented, how did it know your house was cold? How did it know it was hot? How did it know to turn things on and off? Well, it didn't know anything. It doesn't have a brain. It doesn't even have a computer. So this is what the inside looks like. So a mercury switch tilts back and forth in order to turn things on and off. It'll either contact the non-insulated side of the wires, or it won't. If it's contacting them, it completes the circuit and it can flow. That says, hey, turn this thing on. Otherwise, it'll turn it off. This is for a furnace rather than for an air conditioner. And inside that is a bimetallic strip. Now, a bimetallic strip is just, it's exactly what it sounds like. It's a strip made of two metals. The metals expand at different rates, and so when the one expands faster than the other, you get a curl. If the other contracts faster than the other, then you get a curl the other way. Well, you just have a looped up bimetallic strip on the inside of a thermostat that allows it to tilt back and forth. And then you can adjust that using a lever to change how much tilt you need to turn your furnace on and off. You could, of course, do the same thing for an air conditioner. These days, we have much more sophisticated things that don't use a dangerous substance like mercury, but that is how they worked for a very long time. This idea that things will expand when they heat up is called thermal expansion, and the math on it is pretty easy. It is delta L equals alpha L naught delta T. L naught is the original length of the thing. Alpha is called the coefficient of linear expansion. And so the difference in length is just going to be that. The coefficient times the original length times the change in temperature gives you the change in length. You can then add that to the original length to see how much something has expanded, or if you cooled it, then you would subtract that amount from the original amount to see how much it shrank. That's it. If instead of a length you want to do an area, there's a very analogous equation, and for volume there is yet another one. And these coefficients are related to each other. The gamma is 2 alpha and beta is 3 alpha. Basically, the number of dimensions you're working in puts a coefficient of 1, 2, or 3 on your coefficient. And that's pretty much it for thermal expansion. One of the things you can do with thermal expansion, for example, is if you have two pipes that you want to connect together and you don't want them to come apart, You could take a sleeve of a different metal and slide it over them, except that the sleeve is actually too small by, say, 1/1000th of an inch. If you take that sleeve and you heat it up like crazy with a blowtorch, you can then slide it over the one, wear gloves, slide it over the one, put the other one inside, and then let it cool. And as it cools, it'll shrink back down to its original size, and it'll squeeze really tight. You can make really robust, firm joints that are watertight using this process, which is called cold welding, which is neither all that cold, nor is it welding. But there you go. Cold welding is one of many applications. As useful as it is for thermometers and bimetallic strips and things, thermal expansion can also be a really big headache because anything you build is going to expand or contract. If you look at the school building, you'll see that the bricks have cuts in them with some kind of foamy material in between. Those are actually expansion joints. As the walls expand and contract, you want that foam to be able to squish and stretch in order to accommodate. Expansion joints on bridges and things are the same idea. And you really need to factor those into your design because when temperatures swing from mid-February to mid-July, you can get some really big swings in temperature and you can get things to expand and contract, not enough to really see, but oh boy will you see it if you're not paying attention and you build things wrong. Things will break, things will fall apart. It can be very impressive. Now, water behaves in this way generally, except right near freezing. And the exact shape of a water molecule and the fact that they're polar gives you a pretty interesting effect. So you've got this big oxygen with 2 little hydrogen on it, and you get another big oxygen with 2 little hydrogen on it, and in general they're jiggling around like crazy, and the faster they're moving, the higher the temperature, the more they'll jiggle around, and the further apart on average they tend to be. But when you cool them down, they get closer and closer, right? So they shrink. But once you get down below about 4 degrees, they start to line up. The polarity starts to line them up into a crystal structure with some big gaps in between. And this causes water to actually expand right at the freezing point. This causes enormous headaches. It causes potholes. So a little bit of water gets into a crack during the day, it freezes at night, and that water expands, and it can just create huge amounts of pressure and bust up a little bit of concrete or asphalt. The next day, it's a slightly bigger crack. More water gets in, freezes, busts it up again, and so forth. This is why spring and fall is road construction season in Western New York, because you're getting this constant warm during the day, cold at night, warm during the day, cold at night, and it tends to be pretty wet. That combination creates a lot of havoc on our roads. This could cause ice damming in the wintertime as well, where the water can just split your roof open. All sorts of headaches can come, but it also seems to have made life on Earth possible as we know it, so seems like a pretty good trade-off. One more detail for this video. Think about the windows in my classroom. They're really big compared to a window in a house, right? They're pretty skinny, they're just about this much glass. If we wanted to make them a better insulator, so we're losing less heat to the environment, what could we do? We could make them smaller. We could make them thicker. Both of those things would slow down the rate of heat flow, right? Something else we could do is we could just try and keep the room cooler. Trying to keep the room at 62 Fahrenheit when it's minus 10 Fahrenheit outside would not be wasting nearly as much heat as trying to keep the room at 80 Fahrenheit when it's minus 10 Fahrenheit outside, right? Heat's going to transfer faster if there's a bigger temperature difference. Finally, if we could use some kind of glass that's an even better insulator, glass is pretty good, but if we could do an even better insulator, then heat would flow even slower. And so all of these things, it turns out, are linearly proportional to the rate of heat flow. So the rate of heat flow, which we can measure in watts, is equal to a constant we call the thermal conductivity of the material, times the area, times the difference in temperature, divided by its thickness. And the equation, there it is. It's pretty simple. It follows exactly the way you would expect it to for causing something to heat faster or slower through some kind of slab or block or window or wall. And there you go. There are some details of thermodynamics. We're going to move more into gases in particular and how to create work using gas engines in the next couple videos.